Yo, we're gonna attempt to do ray tracing in an hour. Don't know how I'm gonna do this or if I'm gonna do this, but let's see how it goes. This is vaguely based on ray tracing in a weekend, but it's not gonna be exactly the same. Um, but yeah, I'm gonna derive basically everything from scratch, and yeah, why not? So, point of ray tracing is you in real life you have light source, right? And then you have some, let's say, some objects like a sphere. You have light rays, whatever, and they bounce off. Some of them hit your eye, and some of them don't. Now, the fact that some of them don't makes this computation, like, given there's like a lot of like, there's technically infinite light rays, right? There's it doesn't make sense to compute these like all the rays because a lot of the rays you're going to be reflecting off of the object aren't going to be hitting your viewport, or like I guess in this case the eye, aka your camera. So what the ray tracing approach is that you take your camera and you shoot rays out of that, meaning every ray that hits and reflects or whatever, and every ray that doesn't hit is a useful computation, because it means that you're not wasting compute on, like, let's say there was a ray that went that way, right? You're not wasting compute on rays that are guaranteed to not hit, and you know that anything that does hit is guaranteed to be seen by the camera, because it came from the camera, right? So what we can do is we'll model the maths for a bit, which I don't know, if you're bored you could skip ahead, but so what I'll do is I'll just model some Cartesian coordinates. What I'm doing, I'm going to do it in 2D, but it will scale to 3D like the exact same way. So let's say we have a circle right there, and we want to map it using all vector coordinates. I suppose that shouldn't be x and y, that should be I and j, right? Now we know that if it was centered at the origin, we would have all vectors p such that the modulus of p's are, which means that it describes every vector. So let's say r is like 4, right? And here is 4, here's 4. It will describe every vector that has a length of 4. Starting from the origin. Now, our object doesn't need to be starting from the origin, neither does our camera, right? So what we can do is say we offset it by some p minus c, right? Now, p minus c is a vector from c to p. You can think of it that way, as in like the same way that some vector ab is the same as b minus a, aka ob minus oa, where ob is from o to the origin to b and origin to a. So what you can do is, that makes logical sense again, because if it's the vector from c to p, or even p to c, it doesn't actually matter, because again you're doing the modulus. You're describing all vectors that have this length, aka a circle slash sphere. Now, if we define our ray as some vector, right, that starts somewhere, the origin is like where your camera is, where we're looking from, and the direction is the direction in which you're looking. So we say some ray is defined by some a plus tb, where a is the origin, and b is the direction vector. Now t could be some value such that it hits, like in the case that our ray hits the object, t will be that value for which it hits the object, like the exact point. So like in our case, it could be like here, right? And that could be like t equals 0.45 or whatever. Now that means that at t equals 0.45, you could then substitute back into here with your thingies, and then you would get a point at which like that has intersected, your ray has intersected that with the object. Cool. So now, are we doing for time? Okay, yeah, cool. So what we can do is say that, cool, we have what's the equation? P minus c equals r. Now that's not really that useful. Now one of the useful things we can do is square both sides. Now the reason for that is, if you have some dot product, right, that's defined as this, a my handwriting's awful. B, and it's equal to cos theta, where cos theta is the angle between two vectors, right? A, B, and that's theta. Now, what we can do is we could say that A dot B is modulus A modulus B cos theta. But when A is equal to B, we say that, let's say that like B is the same as A, right? So we have A squared cos theta. Well, cos theta, if A and A are the same, then it's 0, right? Cos of 0 is 1, so that just goes away. Now this is quite similar to that. And the dot product is trivial to compute. You just product the components and then sum them. So we can then substitute with this. We now have like P minus C dot P minus C equals R squared. Now, in the case that our ray does hit the object, we know that P will, like, our ray will be P at some point for some T value, right? Like, and we know that P is just a point on the surface, right? Like, and if our ray does intersect, then there exists a T for which the ray has a point on the surface, which means that to solve for that T, we just solve for all rays where the ray is equal to P, aka a point on the surface. I hope that made sense. It might not have, but basically, you're just trying to find all solutions for which this is true. Now, there are some constants here that we can simplify. We could just say that L is equal to A minus C and be like, cool, we have L plus TB dot L plus TB equals R squared. Now, dot product is distributive, so you can just distribute it as you would with any like polynomial or something. Obviously, they're not polynomials, but what we will get is something interesting. It's 2t L dot B plus t squared B dot B is equal to R squared. Now, if I did this correctly, we should have polynomial. Yeah, we do. So if I rearrange this to a more known format, I suppose, we have B dot B t squared plus 2t L dot B plus L dot L minus R squared equals 0. Now, this is your C, this is your, well, 2 times L dot B is your B, and this is your A. So, well, now we have quadratic, right? And, well, so this makes sense, because technically you have two solutions. We only care about the first solution, aka the smaller solution, because, well, I mean, if there's only one solution, then you're a tangent, right? And then you could take whatever solution you actually have. But like, if you're a sphere, right, and you have this thing, and you're shooting a ray, well, yeah, you're gonna hit there, but you're also gonna hit on the other side, and you hitting on the other side is relatively irrelevant for a ray tracer because you're not, like, your eyes aren't looking at the back of it, so it doesn't matter if like there's an intersection at the back. Like, you only care about the one that you see at the front. Cool. Now we can just start from here, right? Because while we could also solve this quadratic based on these values, all we need to know to begin with, at least, is does the sphere hit, or does the ray hit the sphere? And that's relatively trivial to do. So I guess let's start with that. I'm going to be doing this stuff in C++, but you could do whatever you want if you wish to. Let's just do project. And then I also need CMake standard 3 because why not? And CMake compile commands. Compile commands? I forgot what the there you go. And then we could do add an executable. RT-vid set main, nope, main.cpp. Now I should probably create that file and do some, I should probably also create the build files for that, and then do something like this. Yeah, we have C++ 23. We could just use print. I'll just do this at 0 so Clang format doesn't make it look ugly. And then we could use to print then hi. No member name print then instead. Is ClangD just not having a fun time? Let me just restart the language server. Oh, hello. It's a bit strange. Export command, well, that's true. We just RMRF build real quick and because it would be nice to have a I should have C++ 23. It's this CMake export compile commands. I'm just an idiot. Okay, now if I okay, cool. We actually have formatting now. And now if I build this, I'm gonna have build rtvid. Cool. Now the file format we're gonna be using for images is something called I don't actually know what it's called. It's like ppm, I think. I mean the file extension is ppm. But it's a relatively simple file format. If I just create a test of ppm, what it is P3 is one of the formats in which you just have the data as like raw into like integer colors, which is like it makes it as simple as possible. So let's say we have like a I don't know, a 10 by 10 image with a max value of 255. We can then supply 100 colors, right? And every 10 like colors it sees, it will then move on to the next row. It's like really simple. So then what we could do is, if we wish to, we could replicate this like 100 times, right? I mean, there's obviously a better way of doing this, using code, but hey man, this works. It's just for proof of concept. I should only need 101. Cool. So now what I should be able to do is, icat test.ppm. Yeah, cool. So we have a 10 by 10 like square. Cool. So now what we should be able to do is output images, right? Which is also useful, but we want a programmatic way of outputting these images. So I'm just going to create a quick helper, right? Pragma once. I don't know. RT. No, not struct. Space RT. And then I'll create some class ppm. And we'll say that also what attributes do we need for this? We'll need some width, height, I suppose max val as well. But that isn't necessarily needed because in theory you could dynamically say that whatever the max value is, whatever the highest value the like class has ever seen when you've tried to input data into it. I'm not gonna bother with that because it's not worth it for now. Great, Visual Studio Code's being useless. Great, so now we could just do something like m underscore width, m underscore height, max, m underscore max val. Should probably keep that consistent with naming and be like m underscore max val, and then actually do that. What the hell? Okay, cool. So we also now need data, right? We could technically just represent this as a vector. It's a messy way of doing it. There is definitely better ways of doing it, but for now it's okay. And we need some color, right? We need some way of outputting colors. So I'll just put this as data for now. Vector's not used. I mean, it is, but thanks. Well, we can create some struct color. Well, we don't actually need to create a struct color. We could just create a vector, because that will be more useful to us in the future. I'll just do it. I'll just do it like this for now, just in case we need and then what we could say is we have some vector where we have an x, y, and z. What else do we want to be able to do with vectors? We also want to be able to add them. So we can overload an operator saying that vec3 A, vec3 A, vec3 B. Oh, I don't actually need to return a reference. I could just return a copy. Why not? Let's just not follow any good conventions, of course. A dot x plus b dot x. A dot y plus b dot y. A dot z plus b dot z. Great, that's fun. What do you want? Why is it complaining? Is it because it's not a reference? No. Is it because I'm not defining them properly? That would make sense, actually. And then also because it needs to return that. And then what we can do is say that forgot about that. Cool. And then we could do the same for. Well, I don't think we'd ever need to. I don't know. I don't think we're going to need to multiply them necessarily. So what we'll do is we'll do that. And then we'll also do a function called dot. Well, it doesn't take a returner thing. It does take another other though. And then what we're going to return is we're going to do this x times other x plus this y times other y plus this z times other z. And then what else do we need? We should probably also do normalize. You know what, we'll just do this for now and be like we return this divided by the magnitude. That's another thing we need. We do that first. Magnitude should be return good square root of x squared. I mean, you could use pow. I don't think it's particularly worth it in this case. Wow, that's become messy. Then I could just do like, and then do something like that. Cool. And then I'll be like, so I mean, if you don't know, a normal vector is just like, or a normalized vector would just be the unit vector in that direction. Cool. Oh, and then so the reason we did this was for color, I suppose. So now I guess what we can do is type. We can do some type defs, right? We could say that vec3 float or is vec3f. We could say that int32 underscore t And then I guess if you want for completeness, we could also do something like that. And then we could say that some struct color, right? And color inherits from vec3f. And then what we could say is, well, for like, I guess this isn't necessary at all. We could just do something like, this should be an unsigned integer. We could just be like std, yeah, underscore tr. This is like completely unnecessary, but it's just so it's very clear what you're actually doing with the color. Because seeing X, Y, Z on color is a bit strange. So that's just our RGB values. And then we could do all the operations that you want to do. I mean, you're not going to normalize a color, but yeah, it still works. Cool. And then, oh, another thing we should also do is if we're going to output this to a file, we should also operator overload the OStream like thing. So we should be able to do OStream stream and then be like vec3 and t vec, and then we should be able to do stream vec.x vec.y vec. Now the reason I'm doing it with spaces is because calling a protected constructor I shouldn't need to, oh, it's a reference. And then because our value reference can't bind to is that because it's not a that should, I mean, that should be a reference. Yeah, there you go. Cool. I just didn't see that, obviously. Okay, cool. So the reason I've done it with spaces is because the file format output for the ppm file that we're going to have is going to be in the format of RGB with spaces, right? And what the ideal scenario would be was if we have some color called like gray, right? We should be able to just do like gray like that, and we don't have to worry about it. Like instead of doing the whole RGB thing like manually, it just makes it nicer in terms of like usage. So now what we should be able to do is be like, this should reserve like on the constructor, it should reserve the width and height in the vector of m data with some default value. Let's just do black for now, or white. It doesn't actually matter. So what we could do is we could be like constant vector col row and be like, that's the height, no, that's the width, right? And it takes in a default thing. We could say that, cool, yeah, we shouldn't have to necessarily construct this ourselves. We could say that this is 255 and this, right? And then say that we could just do that and it has a default constructor. And then we could say that we want our m underscore data to be, we could just set it to a vector such that the default value is a row, or no, there's height and the default value is a row. Cool. And that will give us a height numbers of rows of like, yeah, you get the idea. Like it will give you a vector that's the width long and you have height of them. So you basically have a coordinate system, aka like the same way your display displays things. So what we can do now is we could say that we set some data, right? you know, 30 underscore t x y, and then we could say we have some color, and we want to set the x and y to color, right? But if the x value is bigger than, or even if it's equal to the width, that's a problem because we're zero indexed, right? Or the y is greater than or equal to height, then we'll say that okay, you know what? This is again a messy way of doing it, but we could just do std throw std runtime except or runtime error and say that um set data out of bounds. And then we could also std format this for debugging purposes, because I mean I'm bound to make some indexing mistake at some point. So do something like that, and then we could just do the x and y. Ah, I'm just an idiot. There you go. Cool. So, and then otherwise we say that the cool. And that should work. So in theory, if we now go on main.cpp and we say that we include this ppm, and we create a file, std of stream test.ppm. I'm just gonna, I can't be bothered to type the import out. And then we say that and we also want to close this file, obviously. So what we do is we create a ppm file with some width and height. Let's just do 300, 300. The max file stays at 255, and we say that we want to be able to write this image to a file. So that's another thing we want to do. So we say stream reference file, and what we should be able to do is say that for int I equals 0, I is less than the width of height even, plus plus, or int j equals 0 is less than width, j plus plus. And then we want to output, well, so first of all, we should output the header, right? It should be a p3 with the width, with a space, height, the space, and max value with a new line. Oh, is it because I haven't included? Oh, it's just F stream, isn't it? Cool. Where was I? Yeah, cool. That can still be a reference. Now, what I need to do is then, now we're on the data section, so we need to output all the colors. So then we just do file output j I, no, ij. Cool. And then we could do a new line for each color, because why not? Let's build that. And then, I mean, we also need to now write it to the file, right? Let's do initial write file, see if that works. I'm assuming that did. Cool. Let's just also test it in our little thing. Great. And then do icat test.ppm. Cool. Now we have a box. I do kind of want to make the default value now black. That was just for testing purposes. because it means that our objects will be clearer to see, like in white. I don't actually like. I don't want to render a black sphere, right? So okay, cool. Now we can actually start implementing our ray tracer. So, uh, you know what? We'll just do it. We'll just do it here. Um, in theory, this should be moved to some math folder or file even. Let me just do that. And then just include. I can also now include various things like CST int OFs. No, just O string, isn't it? And CMath, I suppose. Cool. I also wrap this in that same namespace. Yeah. No, the reason I did this is because I'm about to define what a ray is, right? Now, as we defined, our ray was we had some origin and we had some direction. Cool. And we want to be able to see what the ray is at some point. At some like t, right? Which should just be the origin times, oh no, the origin plus t times the direction. And then now we come to the issue of we haven't defined what multiplication is. So then let's just do something like that. And then that doesn't have an x, y, or z. We could replace that with, and that should fix the problem. Cool. And then we return that. And now we have array. So remember, we want to be able to actually do something with this image. So we're gonna loop through. I'll make the and then do like something like that. And let's loop through the image, pixel by pixel, and cast array, right? That should be another thingy there. Let's do j, nope, width, and j. Cool. And now we wanna. So the general idea is we want to do like if hit sphere, then like image dot set. What did I even call the function? Set data. I j, or I suppose j I to like a green or something, right? Cool. So then now I think we should be able to cast a array in some origin and direction. I'm gonna define the origin for the ray as just 0. And I'm gonna say the direction of the ray is, I don't know, like we're gonna, it's not gonna go up, it's not gonna go down, it's just gonna go like forward. Cool. Now, how do we determine if we pit the sphere? Now that's where our maths comes in, right? So if we let's define some bool, right? And then what do we take? We take in some ray, and we say that the circle has some center at xy. And then we want to see if it oh, and then we also have a center, of course. And we want to return true only if it hits the ray hits the circle or the sphere, I suppose. And now that's satisfied by this equation. Let me just write that down in the like little comment here. We have b dot b t squared 2t l dot b plus l dot l minus r squared. Not so. Oh, we also have a radius. I mean, and then we need to remember that we set L to be a minus c in this scenario. Cool. So, right now the only thing we really care about is if it hits the sphere, not where it hits the sphere. So we're gonna be like, if the discriminant. So if you know about anything about like quadratics, right? If the discriminant is negative, then you can't have any solutions, aka it doesn't hit the sphere. Hence we only care about solutions such that it's greater than or equal to 0, right? So what we can say is we could say delta is it's b squared minus 4ac, right? So in this case, b squared is 2 times l dot b. Now let's define, if we define L as a vec3, and it's a minus c. Now a is the I've realized a problem. This obviously needs to be a vec3f, because we're no longer working in 2D, obviously. So this needs to be a minus c, which is the origin of the ray, subtract the center of the circle, which is trivial to do. Now we also have, what else do I need to define? We have b is, now this is obviously completely useless, me just creating a copy in here. But it's purely for the purposes of showing the equation properly. And we say that b squared minus 4ac, aka delta, is pow. I'm actually going to use pow this time because I don't want to write this massive statement out twice. It's 2 times L dot B squared, right? So this needs to be 2 times L dot B. I haven't marked the dot function as const right now, so these are just not very constant now. It doesn't really actually matter. We're going to say that's B squared, then 4 times B dot B, and C is L dot L subtract radius 2. Cool. And we'll be like, oh shit. If the delta is greater than or equal to 0, then we return true. Oh, we don't actually have to do that. We could just be like, return delta is greater than or equal to 0. Right. And now we can just define a sphere. So if hit sphere ray, we'll define the center as it's going to be not where our camera is, hopefully. It's going to be 0, 0, 40, 100. And it has a radius of 20. Oh, great, I can't spell. If it hits the sphere, then we're going to say image.set data ji to some color. Let's choose green. 0 to 50. No matching constructor. What do you mean? That's peculiar. That should definitely work. I have a constructor for that, don't I know? Ah. I don't think I defined a constructor for it, which is incredibly useful. Um, that's convenient. Let's do X, Y, something like that, right? Cool. So now I can actually, I can actually define the constructors. Something like, um, and say that math folder. No, not math, RT. That should definitely work. Hmm. Hello? It is inheriting from thingy, right? Oh my god, okay, it's because I'm overriding the constructor, that's why. Um, I just don't need to do that. And then I could just be like 3. I'll fix it. Cool. No viable conversion from int to vec3 UI. What? Ah, because now I can actually construct it like this. Expected thingy after. Oh, oh my god. Oh. Where's my ppm? Vec3 UI. You know what? I'll just do something like. And say that because this is obviously the best way of doing things, right? Cool. Well, that was pointless. No matching function call for yes, and now but I've removed the default constructor very usefully. Remember I want this to be 0, so I could just do something like that again. But I mean, there's a better way of doing this actually. I know I didn't say I did say I didn't. It doesn't matter what way we do it, but I wanted to do it like this. Cool. Because I have no reason to define a default constructor unless I actually have to. Okay, cool. Now I can actually define this as green. Great. And otherwise it doesn't matter. So let's try this. See make build. Other has math. Oh, why am I calling this as a pointer? Not that. Cool. So now we render it. Ah, that's useful. Let me make the radius smaller or further away. Let me actually just set that as 1. Huh, radius smaller? 2? Cool. Run it. Render it. Oh, now we have nothing. That's useful. Let's do something like... So the z value for your like ray direction does actually matter. It can determine your FOV. I'm just setting random values for now because I'm hoping to get something that magically works. But clearly this is proving interesting. 3. Oh my god. Still all green. Let me make sure I'm doing this correctly. 2 times L dot B, B squared minus 4 times A times C. Yeah. That's strange. Let me actually set the Z coordinate like 300 away. And we'll say it's 100. Otherwise, I'll actually calculate the what we can do is we can calculate the f of v, like actually, to determine what the like a good value would be for it. You know what? Let's do that. Unless I do like that. Great, that's useful. Origin 0, direction. I've thought of another. I've realized the issue. Okay, cool. So this is a very good point. The other reason this won't work is because we're not using Cartesian coordinates. 0, 0 on this image is not 0, 0 in Cartesian coordinates, and as you should probably realize, this equation is derived using Cartesian coordinates. Cool. So okay, that's good to know. What we can do is define the Cartesian coordinates for this. We can say that it's I minus the height divided by 2, I think. Don't know why I'm putting a semicolon there. And then I think we could do the same thing with j. I mean, I and j need to be swapped because that's not how coordinates work. And that needs to be floating point division. What's the problem? Oh, and then I need to also have a 0 somewhere. Great. Because we don't actually care about the thing. So then the I and j I use as the the other issue. The direction of the ray needs to be the coordinate, which is I obviously forgot to do. Stupidly. Because obviously it's going to be always green if I'm just shooting rays straight at the circle. Cool. Am I missing anything else here? Well, yeah, so now this should not be, it should be Cartesian.x and Cartesian.y. Cool. Am I going to get a circle now? I do get a circle, I think. It's just really far away. Because I messed up everything. All my little, like, values and stuff. Let's make it, like, 50. And our Z coordinate's currently 10. That'll probably do. I think it's better. Certainly better. It's also quite far away, so I'll bring it closer. Oh, there we go. Okay, we actually have a circle now. Now, if we want to calculate the f of v, right? You have to think about this as like, so you are here. This is your direction vector, z coordinate, and your f of v spans from your left to your right, right? Now, let's say you want your f of v to be, I don't know, 90. That means that this value should be 45. Now, we know this value is the width of the screen divided by 2. And we know z is what we're trying to find. And we know that this is just whatever your f of v is divided by 2, because the f of v is whatever spans from the entirety of left to right. But we can just do it from here for now. So what we can do is we could say that tan of is 2z. Also known as width divided by tan of f of v over 2. 2 times that. Cool. And that will give you your z coordinate for any f of v. Now, cool. Let's implement that, because we can say that I want my f of v to, I think the actual f of v, for it to be relatively realistic, should be something between like 0 to 90. Oh no, not 0 to 90. Like 60 to 90 degrees or something. I'll do like 70. This is in degrees, obviously. And we want to convert it to radians, so we'll do a little SG numbers pi divided by 180.f, and we have it in radians because the standard libraries trig functions are in radians. And what we'll do is, well, this needs to be our array because that's our z value. And what we'll do is we'll say our z coordinate is going to be the width of the thing divided by 2 times tan of, or tan f of f of v divided by 2 by f. That shouldn't actually matter, but there we go. And that's our new z coordinate. So if we build that, run it, and cool. Now we actually have a reasonable f of v. And if we increase this, you'll see it does as you would expect, like in a game. Let me actually just do something like that. Cool. It actually does increase the f of v, which is nice. So now we have well, it's a sphere, but you can only see a circle because you're not checking how far the point is you're hitting. You're just checking if you're hitting. Oh, we have 8 minutes. Oh, we can still do some interesting things in 8 minutes. So, okay, we want to find I'm going to speed up a little bit. So we want to find the first solution that we get from solving this quadratic to find the value of c. No, to find the value of t. So what we can do is we say that the first solution is it's minus b plus minus square root of b squared minus 4ac over 2a. So the actual like formula we want to do is minus b minus square root of delta all divided by like that entire thing over 2 times b dot b. Now b is our 2 times l dot b, right? Cool. So then we'll just be like, that's relatively trivial to do. We'll just say it's negative 2 times l dot b minus square root of delta all divided by 2 times b dot b. I think that will give you a first solution. Now another thing we should probably do is like that. If soln is less than 0, and I mean we should only be doing this if it's actually solvable. But if the solution's less than 0, then we find the other solution. And it shouldn't be a const then. Cool. And we should only be doing this if it's actually solvable. Right? Cool. And then we can actually return more than that. We actually return a vec3f, not std vec3f. And then be like, we return nothing, or we return our ray.at our solution, and that will tell us where it hits. Now this is going to be it's going to be a bit weird, but we could just do something like auto solution equals that, and be like, if solution does not equal -1, -1, -1, right? I'll implement. We have 4 minutes. I could do that, right? I'll implement equality. I'll implement equality for vec3. So we could just do, it's not that hard. We could just be like, thingy and thingy and thingy. And then it returns a bool, obviously. Initializer list cannot be used on the right hand side of. There you go. And then cool. And then what we're going to use are the RGB coordinates. So we're actually just going to use as the solution.x, solution.y, solution.z, and we're going to times it by 255. Well, hoping that it's not a negative, but hey ho, if it is. If it is, then we can just like abs it or something. And then what we do is we also just cast it as a color. Well, not as a color, but as an integer. Because we can't have floating point colors, unfortunately. Well, we probably could, but it's out of scope. Let's just do icat test.ppm. Huh, cool. Let me actually we should be able to do this. We should be able to do that, right? I see some of them are negative. Let me just set it to the absolute value for now. So there is a much nicer way of doing this with like diffusion reflection, assuming like it's a matte surface, which I should be able to get to actually. But yeah, there you go. It's not great, but you could kind of tell it sees the sphere. Now let's move if we move our camera like, I don't know, like 10. I should probably move it further away, like 50. Something like this. It's like moved, right? You could see the camera's moved, like 50 right, 50 down. So it's like the sphere is like top right relative to the camera. Which again makes sense. Cool. Yeah. So I mean, we're almost at an hour, but it can be a few minutes over an hour. One of the other things we can do is we could say that yeah, we can get the yeah, this. So as far as I know, we should be able to implement this relatively trivially, because the equation should be like your light level could be represented by your like roughness, like the albedo or whatever. With n dot the normal dot with the light direction. This is not the same L. So the light direction from the object, not from the light, right? But it doesn't actually matter. You can negate them if you wish to think of it in a different way. But so we can implement this relatively easily. If we want the normal for the solution, we could just say that this is normalized, right? Which is probably what I should be doing actually. Because I'm multiplying by 255. What? I haven't defined division either. We quickly do that. But it's the division of a vector and a thing. Cool. It's a vector and then a value, which is the magnitude. Should not be like that. It should be a dot x dot y, a dot z, and something like that. Cool. Great. There we go. We actually have a nice values now. Oh, a nice like color gradient. So if I recenter the camera at 0, 0, I'll also make the FOV like 70 or something. We get a nice sphere. Now let's implement this diffusion thing. So we're just gonna say that the I don't know if I had it. I had the this should be a value between 0 and 1. I'll just set it to 0.5 or something. The normal is just the solution's normalized. Or we can treat it as the solution's normalized and say that we have some vector EF like direction. That's, I don't know, like this. I'm just literally picking random values just for the sake of showing it. And we could say the is the albedo times the solution dot light direction, and instead of doing this we have light level. Now let me actually and this should also be a normalized vector. Nice. There you go. Now we actually have some light. I should also, did I not remove this? Oh. We have some light coming off of the sphere. Let's do like a negative 10, 10, negative 10 or something to see it. Yeah, there you go. That's basic ray tracing in an hour. You could achieve a lot more than this in more hours, obviously. And I don't know how much I actually stayed on track with ray tracing in a weekend or whatever, but yeah, there you go. I think it's relatively like easy to follow. Now, I think this is something that ray tracing in a weekend does as well. Is you abstract away the objects, like you have any hittable object. Like obviously, if you were to load a model, it'll be like a set of triangles or whatever, and then you'd have to figure out how the light actually bounces off of those triangles. And this assumption to make with the whole diffusion material is it doesn't really look that good if you want to make like something like glass, as it says here, like use specular reflection. But yeah, that's ray tracing an hour.